right, so for this video, we're going to be talking about plotting scatter plots and lines of best fit and correlation and causation, all those fun things. So surprisingly, we're not going to use the iris data set. My heart is broken. We're actually going to use the mortar trend car road test data set. This is a data set that's built into R. It's MT cars. And what it is it has 11 different pieces of data that's collected. So miles per gallon, number of cylinders, displacement, total horsepower, real axle ratio, weight, how long it takes it to go a quarter of a mile as fast as possible, I think. This is some categorical data. We're going to look at this later when we do chi-squared testing, but this is engine shape and whether it's an automatic or manual transmission. When you have categorical data, typically it assigns like a 0 or a 1. You'll see this often with male and female. Race, it might be like 0, 1, 2. Those numbers don't mean anything, right? Like a straight engine, well, I don't know if it's better than a V-shaped engine, but the numbers have no value. They're assigned to a category. And we've got the number of gears and number of carburetors. Okay, so let's look at the structure of this data set. So to figure out the structure of a data set, in case it's been a minute, you can type str and then your data set. Look at that. Okay, so it gives me that I've got numbers and what that looks like. I could also type head, MT cars. That gives you the first few lines of your data set and the car type. Apparently not alphabetical. And what I want to talk today is about correlation and causation. So let's think about this data set MT cars. So I think that when we're graphing, right, we have our independent variable, that's our x-axis, and our dependent variable, that's our y-axis. And I'm going to think that weight has an influence on miles per gallon. So let's say I wanted to plot, not a histogram. I mean, if I made a histogram of weight, right, there's a histogram of cars by weight, but I want to compare two data sets. I want to see, does weight have an influence on miles per gallon? And I would, I think it's a good hypothesis that it does. So I would need to plot this. So I'm going to actually plot this. I'm going to plot, I'm going to plot my weight by my miles per gallon. Now let's just see what that looks like real quick. All right, so here's my weight. So as my weight increases, my miles per gallon decreases. This has a negative correlation, right? It has a negative R value. That's what I would expect. And I could go ahead and make this really nice. I could make it blue. Why not? Very fancy. I could give it a title. Car weight. Did I spell weight wrong? I did. Car weight plotted against MPG, miles per gallon. I could label my X label to be car weight. I think it's in tons, right? X label. Car weight by 1,000. That might not be the best way to say it. Car weight by 1,000 pounds. That works. And then my Y label. I don't know, I'm doing Y equals label. Y label could be miles per gallon. Right, so now I have it plotted in blue. And what I want to do is I want to add the line of best fit. So in order for that, I'm going to need to make a linear model. But before we do that, let's talk about core. So core, right? Core computes the variance, the correlation of these matrices. So if I do correlation of the weight of cars by the miles per gallon of cars, right? Error. By both x and y. Oh, I didn't need to do a tilde, I needed to do a comma. All right, so this gives me my correlation. This gives you your R value, right? That gives me my R value. My R value tells me I have strong negative correlation. So let's go ahead and make this a linear model and then plot it against each other. So in order to make a linear model, the order is swapped. So up here, we did our x-axis first, right? We did our x-axis, then y. Here we want to do our y-axis, then x. So I'm going to make a linear model. That's the code LM. And I'm going to do MT cars miles per gallon. So I do my y first, tilde. MT cars weight. Right? That's going to be my linear model. That gives me a line with a x with a slope of negative 5.334 and a y-intercept of 37.285. And that would look to be the case, right? It'd be up here. So that's my linear model. And I need that in order to create my line. So I probably should have done this up here. We'll do it again. I'll copy this and bring it down to show you that you need to do things in order. So you need to define a linear model. You need to make your plot. Then you're going to use the code AB line because I don't know why, but in statistics, they let your slope instead of being M be A. So our A in this case is negative 5.34. And our y-intercept, that's B, the B is the same, is 37.285. So I do AB line of our linear model. So I could go ahead and put in this linear model, or I could name it. I could call it MPG by weight. And then I'd have AB line MPG by weight. See, it pops up. And that symbol, let me show you that again. This little symbol is like your linear model symbol, like it's something you defined. So I could go ahead and plot this. MPG by weight. There we go. Look at this beautiful line. Okay, so here is our line. It would have a y-intercept of 37.285. Now I know that doesn't show up because think about it. If it was the y-intercept, this is not 0. This is probably 1 or a little before, a little after 1. If I had a y-intercept of 0, that means a car that weighed nothing, right, would have a miles per gallon of 37.285, and that doesn't make a lot of sense. I can also, if I wanted to, make this a color, because, you know, we like to be festive, right? Yeah, what else? So if you type in question mark AB line, it'll give you a little bit more information about it. So you've got your A's and your B's. So if I didn't put in a linear model, if I didn't want to do that, I would have gotten the exact same answer if I had, let's type it out, if I had put in AB line with my A equal to negative 5.34 and my B equal to 37. I could have done that as well. Let's run this again. Why didn't that work? Why didn't that work? Yeah, I'm not sure why that didn't work, but it definitely should have. It should have worked, but it did not. Now I'm just being silly. Okay, yeah, it should have worked. There was just probably an issue with the way I entered my numbers. Maybe it didn't like that the y-intercept is off of the graph. That is strange. So let me tell you one other thing. One other way you can define a linear model if you don't want to constantly be calling your data set. So I could also define a linear model as I could have done MPG by weight, comma, data equals MT cars. Equals MT cars. There you go. And I get the exact same data set. It depends on which way you would like to call it. I wanted to say one real last thing, one more thing about correlation, right? So here I've got correlation. I've got a high correlation. This is a high, strong correlation if I had the correct line. Gotta run the whole thing to get rid of the thing. This is a strong negative correlation. In order to see if this really is good data, we're going to want to look at the plots of our linear model. So let me show you what that is going to do. Let's do the plot of MPG by weight. This is actually going to give you four different plots. Okay, so you are seeing here the first of four plots it's going to give you. And what you want, if your data is good, is you want it to have very low residuals. So residuals are the distance from a point on a graph to the line. So if I go back to our first plot, we have our distance from, that's not what I want. That's not what I want at all. There we go. Okay. So notice the residuals. So this would have a positive residual because it's above. Below it would have a negative residual, right? We're looking at the distance from our fitted line. So if I plot my linear model, this right here. Oops. Nope. Go back. Oh, I overshot, y'all. So let's run it again. So I'm taking my residuals versus our fitted. So this is the distance from our best fit line. We want this line to be as straight as possible if we've got really good data. Good data meaning there are no other underlying factors that could be causing this correlation. Remember, correlation is not causation. Even when we are testing or looking for correlation, There could be other external factors or hidden factors. So the first graph is residuals versus fitted. You basically just want this to be as straight of a line as possible. The next graph, normal QQ, what this does is this plots the two sets of quantiles or percentiles versus one another. What you want is you want this to be very, very close to a straight line. And this isn't bad, but our first graph really wasn't so great. The next graph is scale location. And here's what you really want. First, you want this red line to be as horizontal as possible. And you want to look that the spread of the data around the red line doesn't vary so much with the fitted values. What this graph does is it takes the standardized residuals, so it takes our observed minus our expected over the square root of our expected. It's not that complicated, but they have a normal standard deviation. They have a standard deviation of 1, right? And we're trying to get them as close to possible to this line. The last way to see if you've got good data is to look at the residuals versus leverage plot. So this helps us locate outliers whose responses don't follow the general trend line of the rest of our data. And then leverage helps us to locate outliers in terms of our independent variables. So we've got our dependent variable, which was gas, and our independent variable, which is weight. And you can see it's a little bit spread out. And this is just one more of our 4 diagnostic plots. But here's what you really want to know, okay? Any point that lies outside of this dashed line, that's cook distance, that could possibly be an influential point. Meaning this data value 17 right here, this could be a outlier or an error. So the first thing you need to do is verify that any outliers are not errors. The second is try and fit a different regression model, or third, you could even remove this observation, but you have to be very specific about why you're removing the observation and have good reasoning for it, not just because it was an outlier and was messing up your data.